Chapter 13. Aviation Weather Services. Introduction. In aviation, weather service is a combined effort of the National Weather Service, NWS, Federal Aviation Administration, FAA, Department of Defense, DoD, other aviation groups, and individuals. Because of the increasing need for worldwide weather services, foreign weather organizations also provide vital input. While weather forecasts are not 100% accurate, meteorologists, through careful scientific study and computer modeling, have the ability to predict weather patterns, trends, and characteristics with increasing accuracy. Through a complex system of weather services, government agencies, and independent weather observers, pilots and other aviation professionals receive the benefit of this vast knowledge base in the form of up-to-date weather reports and forecasts. These reports and forecasts enable pilots to make informed decisions regarding weather and flight safety before and during a flight. End of page 13-1. Observations. The data gathered from surface and upper altitude observations form the basis of all weather forecasts, advisories, and briefings. There are 4 types of weather observations: surface, upper air, radar, and satellite. Surface aviation weather observations. Surface aviation weather observations, METRs, are a compilation of elements of the current weather at individual ground stations across the United States. The network is made up of government and privately contracted facilities that provide continuous up-to-date weather information. Automated weather sources, such as the Automated Weather Observing Systems, AWOS, Automated Surface Observing Systems, ASOS, as well as other automated facilities, also play a major role in the gathering of surface observations. Surface observations provide local weather conditions and other relevant information for a specific airport. This information includes the type of report, station identifier, date and time, modifier, as required, wind, visibility, runway visual range, RVR, weather phenomena, sky condition, temperature/dew point, altimeter reading, and applicable remarks. The information gathered for the surface observation may be from a person, an automated station, or an automated station that is updated or enhanced by a weather observer. In any form, the surface observation provides valuable information about individual airports around the country. Although the reports cover only a small radius, the pilot can generate a good picture of the weather over a wide area when many reporting stations are viewed together. Air Route Traffic Control Center, ARTCC. The Air Route Traffic Control Center, ARTCC, facilities are responsible for maintaining separation between flights conducted under Instrument Flight Rules, IFR. In the en route structure, center radars, Air Route Surveillance Radar, RSR, acquire and track transponder returns using the same basic technology as terminal radars. Earlier center radars displayed weather as an area of slashes, light precipitation, and HS, moderate rainfall. Because the controller could not detect higher levels of precipitation, pilots had to be wary of areas showing moderate rainfall. Newer radar displays show weather as 3 shades of blue. Controllers can select the level of weather to be displayed. Weather displays of higher levels of intensity make it difficult for controllers to see aircraft data blocks, so pilots should not expect air traffic control, ATC, to keep weather displayed continuously. Upper air observations. Observations of upper air weather are more challenging than surface observations. There are several methods by which upper air weather phenomena can be observed: radius-on observations, pilot weather reports, PIREPs, Aircraft Meteorological Data Relay, AMDR, and the Meteorological Data Collection and Reporting System, MDCRS. A radiosonde is a small cubic instrumentation package that is suspended below a 6-foot hydrogen or helium-filled balloon. Once released, the balloon rises at a rate of approximately 1,000 feet per minute, (fpm). As it ascends, the instrumentation gathers various pieces of data, such as air temperature, moisture, and pressure, as well as wind speed and direction. Once the information is gathered, it is relayed to ground stations via a 300 milliwatt radio transmitter. The balloon flight can last as long as 2 hours or more and can ascend to altitudes as high as 115,000 feet and drift as far as 125 miles. The temperatures and pressures experienced during the flight can be as low as -130 degrees Fahrenheit and pressures as low as a few thousandths of what is experienced at sea level. Since the pressure decreases as the balloon rises in the atmosphere, the balloon expands until it reaches the limits of its elasticity. This point is reached when the diameter has increased to over 20 feet. At this point, the balloon pops and the radiosonde falls back to Earth. The descent is slowed by means of a parachute. The parachute aids in protecting people and objects on the ground. Each year over 75,000 balloons are launched. Of that number, 20% are recovered and returned for reconditioning. Return instructions are printed on the side of each radiosonde. Pilots also provide vital information regarding upper air weather observations and remain the only real-time source of information regarding turbulence, icing, and cloud heights. This information is gathered and filed by pilots in flight. Together, PIREPS and radiosonde observations provide information on upper air conditions important for flight planning. Many domestic and international airlines have equipped their aircraft with instrumentation that automatically transmits in-flight weather observations through the data link system. The Aircraft Meteorological Data Relay, AMDR, is an international program utilizing commercial aircraft to provide automated weather observations. The AMDR program provides approximately 220,000 to 230,000 aircraft observations per day on a worldwide basis utilizing aircraft onboard sensors and probes that measure wind, temperature, humidity/water vapor, turbulence, and icing data. AMDR vertical profiles and en route observations provide significant benefits to the aviation community by enhancing aircraft safety and operating efficiency through improved weather analysis and forecasting. The AMDR program also contributes to improved short and medium-term numerical weather forecasts for a wide range of services including severe weather, defense, marine, public weather and environmental monitoring. End of page 13-2. The information is downlinked either via very high frequency (VHF) communications through the Aircraft Communications Addressing and Reporting System (ACARS) or via satellite link through the Aircraft to Satellite Data Acquisition and Relay (ASTR). The Meteorological Data Collection and Reporting System (MDCRS) is an automated airborne weather observation program that is used in the U.S. This program collects and disseminates real-time upper air weather observations from participating airlines. The weather elements are downlinked via ACARS and are managed by Aeronautical Radio, Incorporated, ARINC, who then forwards them in binary universal form for the representation of meteorological data, BUFR, format to the NWS and in raw data form to the Earth Science Research Laboratory, ESRL, and the participating airline. More than 1,500 aircraft report wind and temperature data, with some of these same aircraft also providing turbulence and humidity/water vapor information. In conjunction with avionics manufacturers, each participating airline programs their equipment to provide certain levels of meteorological data. The monitoring and collection of climb, en route, and descent data is accomplished through the aircraft's Flight Data Acquisition and Monitoring System, FDAMS, and is then transmitted via ACARS. When aircraft are out of ACARS range, reports can be relayed through ASTR. However, in most cases, the reports are buffered until the aircraft comes within ACARS range, at which point they are downloaded. Radar observations. There are 4 types of radars which provide information about precipitation and wind. 1. The WSR-88D NEXRAD radar, commonly called Doppler radar, provides in-depth observations that inform surrounding communities of impending weather. Doppler radar has 2 operational modes, clear air and precipitation. In clear air mode, the radar is in its most sensitive operational mode because a slow antenna rotation allows the radar to sample the atmosphere longer. Images are updated about every 10 minutes in this mode. Precipitation targets provide stronger return signals, therefore, the radar is operated in the precipitation mode when precipitation is present. A faster antenna rotation in this mode allows images to update at a faster rate, approximately every 4 to 6 minutes. Intensity values in both modes are measured in dBz, decibels of Z, and are depicted in color on the radar image. Figure 13.1. Intensities are correlated to intensity terminology, phraseology, for ATC purposes. Figures 13.2 and 13.3. End of page 13.3. 2. FAA Terminal Doppler Weather Radar, TDWR, installed at some major airports around the country, also aids in providing severe weather alerts and warnings to ATC. Terminal radar ensures pilots are aware of wind shear, gust fronts, and heavy precipitation, all of which are dangerous to arriving and departing aircraft. 3. The third type of radar commonly used in the detection of precipitation is the FAA Airport Surveillance Radar. This radar is used primarily to detect aircraft, but it also detects the location and intensity of precipitation, which is used to route aircraft traffic around severe weather in an airport environment. For airborne radar is equipment carried by aircraft to locate weather disturbances. The airborne radars generally operate in the C or X bands, around 6 GHz or around 10 GHz, respectively, permitting both penetration of heavy precipitation, required for determining the extent of thunderstorms, and sufficient reflection from less intense precipitation. Satellite. Advancement in satellite technologies has recently allowed for commercial use to include weather uplinks. Through the use of satellite subscription services, individuals are now able to receive satellite-transmitted signals that provide near real-time weather information for the North American continent. Service outlets. Service outlets are government contract, or private facilities that provide aviation weather services. Several different government agencies, including the FAA, National Oceanic and Atmospheric Administration, NOAA, and the NWS work in conjunction with private aviation companies to provide different means of accessing weather information. Flight Service Station, FSS. The FSS is the primary source for pre-flight weather information. A pre-flight weather briefing from an FSS can be obtained 24 hours a day by calling 1-800-WX-BRIEF from anywhere in the United States and Puerto Rico. Telephone numbers for FSS can be found in the Chart Supplement US, formerly Airport/Facility Directory, or in the United States Government section of the telephone book. The FSS also provides in-flight weather briefing services and weather advisories to flights within the FSS area of responsibility. Telephone Information Briefing Service, TIBS. The Telephone Information Briefing Service, TIBS, provided by FSS, is a system of automated telephone recordings of meteorological and aeronautical information. TIBS provides area and route briefings, airspace procedures, and special announcements. The recordings are automatically updated as changes occur. It is designed to be a preliminary briefing tool and is not intended to replace a standard briefing from a FSS specialist. The TIBS service can only be accessed by a touch-tone phone. The phone numbers for the TIBS service are listed in the Chart Supplement US, formerly Airport/Facility Directory. Hazardous In-Flight Weather Advisory Service, HIWAS. Hazardous In-Flight Weather Advisory Service, HIWAS, available in the 48 conterminous states, is an automated continuous broadcast of hazardous weather information over selected VOR navigational aids, NavAids. The broadcasts include advisories such as AirMets, SIGMETs, convective SIGMETs, and urgent PIREPs. The broadcasts are automatically updated as changes occur. Pilots should contact a FSS or EFAS for additional information. VORs that have HIWAS capability are depicted on aeronautical charts with an H in the upper right corner of the identification box. Figure 13.4. Transcribed Weather Broadcast, TWEB, Alaska only. A continuous automated broadcast of meteorological and aeronautical data over selected low or medium frequency, L/MF, and very high frequency, VHF, omnidirectional range, VOR, NavAid facilities. The broadcasts are automatically updated as changes occur. The broadcast contains adverse conditions, surface weather observations, PIREPs, and a density altitude statement, if applicable. Recordings may also include a synopsis, winds aloft forecast, en route and terminal forecast data, and radar reports. At selected locations, telephone access to the TWEB has been provided. Tel TWEB. Telephone numbers for this service are found in the Alaska Charts Supplement US, formerly Airport/Facility Directory. These broadcasts are made available primarily for pre-flight and in-flight planning, and as such, should not be considered as a substitute for specialist-provided pre-flight briefings. End of page 13-4. Weather briefings. Prior to every flight, pilots should gather all information vital to the nature of the flight. This includes an appropriate weather briefing obtained from a specialist at a FSS. For weather specialists to provide an appropriate weather briefing, they need to know which of the three types of briefings is needed: standard, abbreviated, or Outlook. Other helpful information is whether the flight is Visual Flight Rules, VFR, or IFR, Aircraft Identification and Type, Departure Point, Estimated Time of Departure, ETD, Flight Altitude, Route of Flight, Destination, and Estimated Time en route, ETE. This information is recorded in the flight plan system and a note is made regarding the type of weather briefing provided. If necessary, it can be referenced later to file or amend a flight plan. It is also used when an aircraft is overdue or is reported missing. Standard briefing. A standard briefing provides the most complete information and a more complete weather picture. This type of briefing should be obtained prior to the departure of any flight and should be used during flight planning. A standard briefing provides the following information in sequential order if it is applicable to the route of flight. 1. Adverse conditions. This includes information about adverse conditions that may influence a decision to cancel or alter the route of flight. Adverse conditions include significant weather, such as thunderstorms or aircraft icing, or other important items such as airport closings. 2. VFR flight not recommended. If the weather for the route of flight is below VFR minimums, or if it is doubtful the flight could be made under VFR conditions due to the forecast weather, the briefer may state VFR flight not recommended. It is the pilot's decision whether or not to continue the flight under VFR, but this advisory should be weighed carefully. 3. Synopsis and overview of the larger weather picture. Fronts and major weather systems that affect the general area are provided. For current conditions, the current ceilings, visibility, winds, and temperatures. If the departure time is more than 2 hours away, current conditions are not included in the briefing. 5. En route forecast, a summary of the weather forecast for the proposed route of flight. 6. Destination forecast, a summary of the expected weather for the destination airport at the estimated time of arrival, ETA. 7. Forecast winds and temperatures aloft, a forecast of the winds at specific altitudes for the route of flight. The forecast temperature information aloft is provided only upon request. 8. Notices to airmen, NOTAM, information pertinent to the route of flight that has not been published in the NOTAM publication. Published NOTAM information is provided during the briefing only when requested. 9. ATC delays, an advisory of any known ATC delays that may affect the flight. 10. Other information. At the end of the standard briefing, the FSS specialist provides the radio frequencies needed to open a flight plan and to contact EFAS. Any additional information requested is also provided at this time. Abbreviated briefing. An abbreviated briefing is a shortened version of the standard briefing. It should be requested when a departure has been delayed or when weather information is needed to update the previous briefing. When this is the case, the weather specialist needs to know the time and source of the previous briefing so the necessary weather information is not omitted inadvertently. It is always a good idea for the pilot to update the weather information whenever he/she has additional time. Outlook briefing. An Outlook briefing should be requested when a planned departure is 6 hours or more away. It provides initial forecast information that is limited in scope due to the time frame of the planned flight. This type of briefing is a good source of flight planning information that can influence decisions regarding route of flight, altitude, and ultimately the go/no-go decision. A prudent pilot requests a follow-up briefing prior to departure, since an outlet briefing generally only contains information based on weather trends and existing weather in geographical areas at or near the departure airport. A standard briefing near the time of departure ensures that the pilot has the latest information available prior to his/her flight. Aviation weather reports. Aviation weather reports are designed to give accurate depictions of current weather conditions. Each report provides current information that is updated at different times. Some typical reports are METRs and PIREPs. End of page 13 to 5. Aviation Routine Weather Report, METR. A METR is an observation of current surface weather reported in a standard international format. While the METR code has been adopted worldwide, each country is allowed to make modifications to the code. Normally, these differences are minor but necessary to accommodate local procedures or particular units of measure. This discussion of METR covers elements used in the United States. METRs are issued on a regularly scheduled basis unless significant weather changes have occurred. A special METR, SPICY, can be issued at any time between routine METR reports. Example: METR KGGG 1617530 Auto 14021 G26 KT3/4SM plus TSRABR BKN 008 OVC 012 CB 1817 SE 2970 RMK Press for. A typical METR report contains the following information in sequential order. 1. Type of report. There are two types of METR reports. The first is the routine METR report that is transmitted on a regular time interval. The second is the aviation selected SPICY. This is a special report that can be given at any time to update the METR for rapidly changing weather conditions, aircraft mishaps, or other critical information. 2. Station Identifier. A four-letter code is established by the International Civil Aviation Organization, ICAO. In the 48 contiguous states, a unique three-letter identifier is preceded by the letter K. For example, Gregg County Airport in Longview, Texas, is identified by the letters KGGG, K being the country designation and GGG being the airport identifier. In other regions of the world, including Alaska and Hawaii, the first two letters of the four-letter ICAO identifier indicate the region, country, or state. Alaska identifiers always begin with the letters PA and Hawaii identifiers always begin with the letters PH. Station identifiers can be found by calling the FSS, NWS office, or by searching various websites such as DUITS and NOAA's Aviation Weather Aviation Digital Data Services, ADDS. 3. Date and time of report, depicted in a 6-digit group, 161753Z. The first two digits are the date. The last four digits are the time of the METR/SPICY, which is always given in Coordinated Universal Time, UTC. A Z is appended to the end of the time to denote the time is given in Zulu time, UTC, as opposed to local time. For modifier, denotes that the METR/SPICY came from an automated source or that the report was corrected. If the notation auto is listed in the METR/SPICY, the report came from an automated source. It also lists AO1 for no precipitation discriminator, or AO2 with precipitation discriminator in the remarks section to indicate the type of precipitation sensors employed at the automated station. When the modifier COR is used, it identifies a corrected report sent out to replace an earlier report that contained an error, for example, METR KGGG 1617530 COR. 5. Wind reported with 5 digits, 14021 kT, unless the speed is greater than 99 knots, in which case the wind is reported with 6 digits. The first 3 digits indicate the direction the true wind is blowing from in tens of degrees. If the wind is variable, it is reported as VRB. The last 2 digits indicate the speed of the wind in knots unless the wind is greater than 99 knots, in which case it is indicated by 3 digits. If the winds are gusting, the letter G follows the wind speed, G26 kT. After the letter G, the peak gust recorded is provided. If the wind direction varies more than 60 degrees and the wind speed is greater than 6 knots, a separate group of numbers, separated by a V, will indicate the extremes of the wind directions. 6 is visibility. The prevailing visibility, 3/4 sm, is reported in statute miles as denoted by the letters sm. It is reported in both miles and fractions of miles. At times, runway visual range, RVR, is reported following the prevailing visibility. RVR is the distance a pilot can see down the runway in a moving aircraft. When RVR is reported, it is shown with an R, then the runway number followed by a slant, then the visual range in feet. For example, when the RVR is reported as R17L/1400 FT, it translates to a visual range of 1,400 feet on runway 17 left. 7. Weather can be broken down into two different categories, qualifiers and weather phenomenon, plus TSRABR. First, the qualifiers of intensity, proximity, and the descriptor of the weather are given. The intensity may be light, moderate, or heavy, plus. Proximity only depicts weather phenomena that are in the airport vicinity. The notation VC indicates a specific weather phenomenon is in the vicinity of 5 to 10 miles from the airport. Descriptors are used to describe certain types of precipitation and obscurations. Weather phenomena may be reported as being precipitation, obscurations, and other phenomena, such as squalls or funnel clouds. Descriptions of weather phenomena as they begin or end in hailstone size are also listed in the remarks sections of the report. Figure 13, 5. End of page 13 to 6. 8. Sky condition, always reported in the sequence of amount, height, and type or indefinite ceiling/height, vertical visibility, BKN 008 OVC 012 CB, VV 003. The heights of the cloud bases are reported with a 3-digit number in hundreds of feet AGL. Clouds above 12,000 feet are not detected or reported by an automated station. The types of clouds, specifically towering cumulus, TCU, or cumulonimbus, CB, clouds, are reported with their height. Contractions are used to describe the amount of cloud coverage and obscuring phenomena. The amount of sky coverage is reported in eighths of the sky from horizon to horizon. Figure 13, 6. 9. Temperature and dew point. The air temperature and dew point are always given in degrees Celsius, C, or 18/17. Temperatures below 0 degrees Celsius are preceded by the letter M to indicate minus. 10. Altimeter setting, reported as inches of mercury, Hg, in a 4-digit number group, A2970. It is always preceded by the letter A. Rising or falling pressure may also be denoted in the remarks sections as PRESRR or PRSFR, respectively. 11. Zulu time, a term used in aviation for UTC, which places the entire world on one time standard. 12. Remarks. The remarks section always begins with the letters RMK. Comments may or may not appear in this section of the matter. The information contained in this section may include wind data, variable visibility, beginning and ending times of particular phenomenon, pressure information, and various other information deemed necessary. An example of a remark regarding weather phenomenon that does not fit in any other category would be OCNLCHIC. This translates as occasional lightning in the clouds and from cloud to ground. Automated stations also use the remarks section to indicate the equipment needs maintenance. Example: Meter KGGG 1617530 Auto 14021 G26 KT 3/4 SM plus TSRABR BKN 008 OVC 012 CB 1817 say 2970 RMK press for. End of page 13 to 7. Explanation. Routine meter for Gregg County Airport for the 16th day of the month at 17:53 Z automated source. Winds are 140 at 21 knots gusting to 26. Visibility is 3/4 statute mile. Thunderstorms with heavy rain and mist. Ceiling is broken at 800 feet, overcast at 1,200 feet with cumulonimbus clouds. Temperature 18 degrees Celsius and dew point 17 degrees Celsius. Barometric pressure is 29.70 Hg and falling rapidly. Pilot weather reports, PIREPs. PIREPs provide valuable information regarding the conditions as they actually exist in the air, which cannot be gathered from any other source. pilots can confirm the height of bases and tops of clouds, locations of wind shear and turbulence, and the location of in-flight icing. If the ceiling is below 5,000 feet, or visibility is at or below 5 miles, ATC facilities are required to solicit PIREPs from pilots in the area. When unexpected weather conditions are encountered, pilots are encouraged to make a report to a FSS or ATC. When a pilot weather report is filed, the ATC facility or FSS adds it to the distribution system to brief other pilots and provide in-flight advisories. PIREPs are easy to file and a standard reporting form outlines the manner in which they should be filed. Figure 13.7 shows the elements of a PIREP form. Item numbers 1 through 5 are required information when making a report, as well as at least one weather phenomenon encountered. A PIREP is normally transmitted as an individual report but may be appended to a surface report. Pilot reports are easily decoded, and most contractions used in the reports are self-explanatory. Example: UA/OVGG090025/TM1450/FL060/TP-C182/FL060/TBLGT/RMV rain. Explanation: Type: Routine pilot report. Location: 25 nm out on the 090-degree radial, Gregg County, VR. Time: 1450 Zulu. Altitude or flight level: 6,000 feet. Aircraft type: Cessna 182. Sky cover: 8000 overcast. Visibility/weather: 4 miles in rain. Temperature: 5 degrees Celsius. Wind: 270 degree at 30 knots. Turbulence: light. Icing: none reported. Remarks: rain is heavy. End of page 13-8. Aviation forecasts. Observed weather condition reports are often used in the creation of forecasts for the same area. A variety of different forecast products are produced and designed to be used in the pre-flight planning stage. The printed forecasts that pilots need to be familiar with are the Terminal Aerodrome Forecast, TAF, Aviation Area Forecast, FA, In-Flight Weather Advisories, SIGMET, AirMet, and the Winds and Temperatures Aloft Forecast, FB. Terminal Aerodrome Forecasts, TAF. A TAF is a report established for the 5 statute mile radius around an airport. TAF reports are usually given for larger airports. Each TAF is valid for a 24 or 30-hour time period and is updated 4 times a day at 0000Z, 0600Z, 1200Z, and 1800Z. The TAF utilizes the same descriptors and abbreviations as used in the meta report. The TAF includes the following information in sequential order. 1. Type of report: a TAF can be either a routine forecast, TAF, or an amended forecast, TAF-AMD. 2. ICAO station identifier: the station identifier is the same as that used in a METR. 3. Date and time of origin: time and date, 081125Z, of TAF origination is given in the 6 number code, with the first 2 being the date, the last 4 being the time. Time is always given in UTC as denoted by the Z following the time block. For valid period dates and times, the TAF valid period, 0812/0912, follows the date, time of forecast origin group. Scheduled 24 and 30-hour TAFs are issued 4 times per day, at 0000, 0600, 1200, and 1800Z. The first 2 digits, 08, are the day of the month for the start of the TAF. The next 2 digits, 12, are the starting hour, UTC. 09 is the day of the month for the end of the TAF, and the last 2 digits, 12, are the ending hour, UTC, of the valid period. A forecast period that begins at midnight UTC is annotated as 00. If the end time of a valid period is at midnight UTC, it is annotated as 24. For example, a 00Z TAF issued on the 9th of the month and valid for 24 hours would have a valid period of 0900/0924. 5. A forecast wind: the wind direction and speed forecast are coded in a 5-digit number group. An example would be 15011 kT. The first 3 digits indicate the direction of the wind in reference to true north. The last 2 digits state the wind speed in knots appended with kT, like the meter. Winds greater than 99 knots are given in 3 digits. 6. Forecast visibility, given in statute miles and may be in whole numbers or fractions. If the forecast is greater than 6 miles, it is coded as P6SM. 7. Forecast significant weather phenomena are coded in the TAF reports in the same format as the meter. 8. Forecast sky condition, given in the same format as the meter. Only cumulonimbus (CB) clouds are forecast in this portion of the TAF report as opposed to CBs and towering cumulus in the meter. 9. Forecast change group, for any significant weather change forecast to occur during the TAF time period. The expected conditions and time period are included in this group. This information may be shown as from FM and temporary tempo. FM is used when a rapid and significant change, usually within an hour, is expected. Tempo is used for temporary fluctuations of weather, expected to last less than 1 hour. 10. Prob 30, a given percentage that describes the probability of thunderstorms and precipitation occurring in the coming hours. This forecast is not used for the first 6 hours of the 24-hour forecast. Example: TAF KPIR 111130Z1112/1212 Tempo 1112/1114.5 SMBR FM 1500-16015 G25 KTP6 SMSCT 040 BKN 250 FM 12000014012 KTP6 SMBKN 080 OVC 150 Prob 30 1200/12043 SMTSRA BKN 030 CB FM 120400408 KTP6 SMSCT 040 OVC 080 Tempo 1204/12083 SMTSRA OVC 030 CB Explanation. Routine TAF for Pierre, South Dakota, on the 11th day of the month, at 11:30 Zulu, valid for 24 hours from 1200 Zulu on the 11th to 1200 Zulu on the 12th, wind from 150 degrees at 12 knots, visibility greater than 6 sm, broken clouds at 9,000 feet, temporarily, between 1200 Zulu and 1400 Zulu, visibility 5 statute miles in mist, from 1500 Zulu winds from 160 degrees at 15 knots, gusting to 25 knots, visibility greater than 6 statute miles, clouds scattered at 4,000 feet and broken at 25,000 feet, from 0000 Z wind. From 140 degrees at 12 knots, visibility greater than 6 sm, clouds broken at 8,000 feet, overcast at 15,000 feet, between 0000 Zulu and 0400 Zulu, there is 30% probability of visibility 3 statute miles, thunderstorm with moderate rain showers, clouds broken at 3,000 feet with cumulonimbus clouds. From 0400 Zulu, winds from 140 degrees at 8 knots, visibility greater than 6 miles, clouds at 4,000 scattered and overcast at 8000, temporarily between 0400 Zulu and 0800 Zulu, visibility 3 miles, thunderstorms with moderate rain showers, clouds overcast at 3,000 feet with cumulonimbus clouds, end of report, =. End of page 13 to 9.